Good afternoon, everyone. The paper I'm going to present today is titled A Robot That Plays Rubik's Race, a Slide Puzzle Game. My name is Chang Duan, and an associate professor in the Department of Mechanical Engineering at Prairie View A&M University. And this is a collaborative research with the University of New York at Buffalo. I would like to thank my co-author, Sankit Anupam Nikhil, and Professor Junsong Yuan. So what is the motivation of this research? Um, as we will discuss later, Rubik's Race is a slide puzzle game, and games have been a proving ground for artificial intelligence, from Deep Blue to AlphaGo. These human versus AI events have always illustrated um, the advancement of AI and captured the public's attention. Despite the success of playing games in the digital world, though, it is considerably more challenging for the machine to play games physically, especially when both real-time computing and agility are required. So one can try to make a specialized machine, right, to excel at playing one type of game. Uh, while it may not be easy to repurpose that machine for other tasks, or one can adapt a general purpose machine to play the game. And that is what we choose to do, right? So we adapt a general purpose robot arm to play this game. Lastly, this research um, provides educational value, right? As it is a multidisciplinary research, um, and many students are trained using this project. Um, all right, so now let's talk about the game. The Rubik Race game is a two players slide puzzle game. Um, there is a scrambler which is shown um, on top of this figure, and the game begins with shaking this scrambler. The scrambler contains nine cubes with different colors on each side. So six different colors in total. As a result, a random three by three color pattern is generated. Then player A and player B um, then slide the color tiles in their own tray, right? And compete until the nine tiles in the center, matches those in the scrambler. So each tray basically contains 24 tiles, so four of each color, and an empty space arranged in a five row, five column pattern. Um, so basically, the faster player achieve the um, results by matching the central three by three with the scrambler wins the game. Right, so that's the game. All right, so let's move on now to the literature. So as far as we know, there is no robot has been built to play the Rubik's race game before. Similar works can be found in the popular Rubik's race game. Sorry, Rubik's cube game, right? This is a Rubik's cube game. There are many algorithms developed for solving the uh, Rubik's cube. Um, and in 2016, Infineon developed a robot specifically to solve a Rubik's cube and achieves under 1 second time using that specialized machine. And in 2 years later, right, MIT students has improved the motors and control for the machine, and that machine can solve the cube in less than 0.4 seconds time. Then in 2019, OpenAI tapped into the power of modern artificial intelligence and built a robotic hand called Dactyl. So this robotic hand learned to solve the Rubik's cube through try and error in simulation. Another group of similar works are the research on solving n squared minus 1 puzzle. One example of such puzzle is the 15 puzzle, which is pretty popular in the United States, invented in late 19th century. So for the 15 puzzle, right? So the goal is to arrange the number 1 to 15, right? In this sequentially, right? In this 4 by 4 uh, 4 row 4 columns pattern, right? With a random shuffle start. Yeah, so for the 15 puzzle, iterative deepening A star using additive pattern database as heuristics can find the optimal solution in a reasonable time. Um, in general, there is a trade-off between the optimality of the solution, that is to say, the number of moves needed to reach the goal state and the computational efficiency, right? And there's yeah, for the n squared minus 1 puzzle, there's no robotic implementation that we have found in the literature. So our contribution is that we have developed 2 algorithms to solve the Rubik's race puzzle and also adapt a general purpose robotic arm to play the game autonomously. Okay, so let's talk about the first algorithm to solve this Rubik's race puzzle, right? Yeah, the first algorithm is the iterative deepening A star using additive pattern database as heuristics. So this algorithm has 2 steps. So there's an offline step to generate the pattern database, and there's a online part. So some background on this is the color tiles, right? We previously see the color tiles for this game on the tray is mapped into numbers, right? Since only the 9 tiles in the center, right, has to match the scrambler, so they are assigned distinct numbers, right? So there's 7, 8, 9, 12, 13, 14, 17, 18, 19. While all the other tiles are assigned number 1, and 0 represents the empty space. So that is the goal state of this algorithm, right? So basically, for the pattern database generation, we start from this goal state and shuffle through all the permutations and track the minimum count of steps for each permutation. And we store the permutation and the minimum count into a database. So this becomes the heuristics when we are um, doing the online search. Okay. Um, yeah. So now at runtime, right? This at runtime, um, it follows the iterative deepening A star algorithm, which I will briefly explain here. So first, let's talk about the symbols here. So H is the heuristic function, which is given by looking up the pattern database we generated offline. It's basically an estimation of um, the number of moves, right, from the current state to the goal state. And G is the moves taken from the initial states to the current states. So F is a summation of H and G. Um, so that's the best guess for the total moves. Um, and there's a bound, which is the upper limit of the expected moves. And mean is the best estimated paths among all the children of the current state. Okay, so let's say we have this, the figure here shows the one initial state, right? Um, and let's say the estimated guess for remaining books moves for this state from the pattern database is H equals to 38. Uh, so we first will set the bound to 38, right? That's the best estimate we have, and we don't have any minimum yet, since we haven't explore any of the children paths. Okay, so from here, there's a different move you can take, right? So let's say when you move this number eight, right, to right. Yeah, this is an empty space. Move number eight to the right. So for this state, the heuristics look up the pattern database tell us it's a 39. Then we spend one move to go from the initial state to here. So G equals to 1 and add them up, F equals to 40. Um, yeah, so 40 is greater than the bound 38. So we're basically stop exploring this path and move on to and meanwhile also set the minimum to minimum we have so far to 40, then move on to the next children node of the current state. Yeah, so next possibility is moving one to the left, right? So now we can see that we have a age 37, G equals to 1, F is 38. So this is equals and equals the bound. So we can keep exploring the children node of this branch. Um, yeah, so one of the move after at this current state, the next move can be moving 12 to the left, right? So let's say the age and age is 38, right? We take two moves from the initial move to here, so G is 2. The total is 40. 40 um, is greater than the bound. So we're going to stop looking at uh, these children, right? Then we should go back to explore other possibilities like moving one down or moving this one down or moving one up. But if after all the exploration we cannot get better f or smaller f than 40, we'll basically go back here and change the minimum, change the bound to the minimum, right? So set the bound to 40 and repeat this process until we find the best, the shortest path to reach the goal state. So that is the basic idea of iterative deepening A star. All right. Yeah, so the second algorithm is called sequential path planning with A star search. Um, yeah, so for this algorithm, we can see the 3 by 3 target pattern or goal pattern is one example is on this right hand side of the figure. So it has 9 positions: 1, 2, 3, 4, 5, 6, 7, 8, 9. Um, then the puzzle pattern has 25 positions showing on the left, right? So um, the yeah, the idea of this algorithm is to look at one position at a time. So let's say we look at one position, number one of the target pattern has a white tile, right? So position 7 over here, we have to match that white tile, right? Um, and we want to find the minimum number of moves to do that, right? So in this case, in this example, happened at 7 is already a white tile, so we're going to move on to the next position. The next position, if we say we want to have blue, right? We want to have a blue at number 8, right? Position number 8 on the puzzle pattern here. Um, so we're going to find the nearest blue tile, in this case over here, right above 8. And we're going to um, simulate the moves, right? To check how many moves, using the A star search to check how many moves we need to place 3 at 8. Um, However, we're going to keep 7 as an obstacle. So 7 will not be moved, right? Because it's already in the correct location. Um, yeah, so that's um, the second position, right? Then after you move the blue to 8, you're going to continue to move white to number 9 position, while treating the tiles at 7 and 8 as obstacles. Um, and like this, we're going through all the 9 positions, and we keep track of the total number of moves needed. All right. Um, yeah, so this is just one sequence, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. So to optimize this search to find potential smaller number of total number of moves, we basically explore randomly generated other sequences. So let's say we can also place white at 1 first, then play the red at 4, then place the green at 7, so on and so forth. So that's another sequence, right? So when we explore more sequences, potentially we can find a shorter amount of total moves. Then we pick the shortest, the smallest number of moves to execute the algorithm. So that's the idea for this sequential path planning. Okay. Yeah, so to test the the 2 algorithms, we generated 625 test cases from the permutation of 25 initial puzzle pattern and 25 goal patterns. And the result is summarized in the table, right? The PDB algorithm stands for the pattern database based algorithm, and SPA stands for the sequential path planning with a star search. And the number after SPA is uh, number the number of sequences we sampled. So like I explained just now, we generate random sequences so that we can potentially find shorter amount of smaller amount of moves to do it. So there's 50 samples, 100 samples, 200 samples, and 500 samples. Okay, yeah, so we can see the the pattern database generally gives the shortest solution in terms of steps. However, the time needed to find a solution, uh, we can say is on average is longer than SPA algorithm, and main thing is not very consistent time. So some certain cases will take longer, some cases shorter time. So this pie chart shows you basically the distribution of solving times for pattern database, right? So we can see there's 55% of the 625 cases it takes only less than 10 seconds. Um, but there's still like 11%, 9 plus 2 takes more than 100 seconds to solve, to find a solution. So that is not ideal, not desirable if you want to implement it in real time. Um, okay, so for the SPA algorithm, we can see the time is very consistent, and it's basically looks proportional to the number of samples we generated. Um, so the trade-off is between the steps of the solution and the time taken to find the solution. So based on the computational power available, you can choose to uh, use the number of sequences sample to strike a balance between the time efficiency and the solution efficiency. So to develop a time efficient algorithm that can give an optimal or near optimal solution is a future direction of research. All right, so a little bit about the robot. So the robot is not built by us. It's an off-the-shelf robot from Yabun. And it's a 5 degree of freedom robot. But for our purpose, we didn't really rotate the gripper. So we treat it as a 4 degree of freedom as denoted here, the four links L1, L2, L3, and L4 um, are used in our kinematics calculation. So this slide lists some of the major parameters of the robot. Yeah, I should mention we actually also replaced the camera. Uh, we replaced the original camera, so the new camera will have a larger field of view. All right, so some other modifications we did is we did add magnet to the puzzle, right? In the sense that the tray has a magnet, and each puzzle piece is also has a magnet. Um, so the sliding can be more robust, right? The positioning of the tiles can be a little bit more robust. Yeah, so we did 3D printed many parts here to help this process. All right, so let's look at a video demonstration here. All right. So with this, I concludes my presentation. And if you have any question or suggestions, please feel free to contact me. This is my email address. All right. Thank you.